Ever wondered about the peculiarities of quantum mechanics? Why does an electron behave both like a particle and a wave? Is there a way to make sense of this? You see, the quantum world is a peculiar place where particles can exist in multiple states and places at once. But what if there was a theory that could offer a more intuitive understanding of these phenomena? Well, let's dive into the fascinating world of quantum mechanics and explore the pilot wave theory. Our story begins in 1927 with Louis de Broglie, a French physicist. A man of vision and insight, de Broglie dared to look at the world of the infinitesimally small in a new light. He was the first to propose the concept of wave-particle duality, a radical idea that suggested particles of matter could also exhibit properties of waves. This was the spark that ignited the genesis of the pilot wave theory. De Broglie's perspective was a departure from the conventional wisdom of his time. He proposed that particles, those elusive inhabitants of the quantum realm, always possess specific positions and velocities. This was a stark contrast to the prevailing Copenhagen interpretation, which suggested particles existed in a state of superposition, being simultaneously in numerous states until measured. This early work by de Broglie was the seed of an idea that would challenge our understanding of the quantum world. But the pilot wave theory was just getting started. Enter David Bohm, an American physicist, who took the baton from de Broglie in 1952. Bohm breathed new life into the pilot wave theory, expanding it to include an intriguing new element, the pilot wave. This wave, he proposed, exists in a high-dimensional configuration space and guides particles, influencing their trajectory. Now, let's delve a bit deeper and see this theory in action through the lens of the double-slit experiment, a cornerstone of quantum mechanics. Traditionally, this experiment has been explained by the Copenhagen interpretation, suggesting that particles exist in a superposition of states, passing through both slits simultaneously until observed. But Bohm had a different view. According to the pilot wave theory, each particle takes a path through one slit only, while the pilot wave, this unseen guide, passes through both. What we see as an interference pattern on the screen isn't the result of a particle's superposition, but from the self-interference of the pilot wave. This wave, like a shepherd guiding its flock, directs particles to form the pattern we observe. This perspective is quite a departure from conventional quantum mechanics. It doesn't just describe particles as having a probability of being in one state or another. Instead, it provides a deterministic framework where particles always have definite positions and velocities, guided by the pilot wave. And thus, the pilot wave theory offered a new way to look at quantum phenomena. It challenges us to rethink our understanding of the quantum domain and the very nature of reality itself. The pilot wave theory, though appealing in its determinism and predictability, is not without its critics. This theory's deterministic framework suggests that if we knew all initial conditions, that is, particle positions, velocities, and waveforms, we could predict quantum phenomena with precision. This is a stark contrast to the probabilistic outlook of the Copenhagen interpretation. Another intriguing implication of Bohemian mechanics is its embrace of non-locality. This concept, where distant particles can instantly affect each other's state, aligns with observations of quantum entanglement. It's as if the particles are interconnected through the pilot wave, dancing to the same cosmic tune, no matter how far apart they might be. But as with any theory, there are challenges and critiques. One of the main criticisms that the pilot wave theory faces is the complexity it introduces, particularly in systems with many particles. To understand this, imagine trying to choreograph a ballet where every dancer is not only performing their own steps, but also influencing and being influenced by every other dancer on the stage. Additionally, the theory's reliance on a high-dimensional configuration space for the pilot wave is seen as a significant theoretical burden. It's like trying to navigate a maze with countless dimensions, a task that is as fascinating as it is daunting. Despite these challenges, the pilot wave theory continues to provoke thought and debate among physicists. Its deterministic nature and the concept of a guiding pilot wave invite us to rethink our understanding of the quantum world. So, where does this leave us in our quest to understand the quantum world? With the pilot wave theory, we're offered a deterministic wave-particle duality-based framework. No more superposition of states, but definite positions and velocities guided by a pilot wave. It's a challenge to traditional interpretations and a fresh invitation to rethink the foundational nature of the quantum domain. The pilot wave theory, indeed, offers an intriguing perspective, a different lens to view the quantum world. The quantum conversation continues, and so does our quest to unravel the mysteries of the universe.